Okay, so here's what we were talking about last time, talking about second-order partials, and to the question of, well, what do they look like, right? A couple of them are easy, right? Now, of course, all of this is, we're talking about functions of two variables in order to be able to visualize them, because if you have two input variables and one output variable, that's already three variables. That's the most variables we can pretend to have on an axis system at once and have any geometric intuition. So if you want to look at a graph and think in terms of slopes and stuff like that, we're pretty much limited to two variables. So conveniently, second partials with respect to a single variable like fxx, it's really geometrically satisfying. We're holding y constant for the whole calculation. So we're looking in that plane. And for example, if this cross-section is concave down, you're going to have a negative second partial. Okay, so we talked about that last time. This does not help us understand what we call the mixed second partials. So what if I want to do fxy or fyx or something like that, right? I can't just say, oh, well, it's single variable calculus because one of the variables is just constant. No, it isn't, right? So let's look at, for example, here, this mixed second partial. For part of the calculation, x is being held constant. After that, it isn't. It's the variable, and y is being held constant. So this is not a single variable calculus problem. What we're about to see here is not just, analogous to something you saw in Calc 1, right? And there's a few instances in multivariable calculus where things that are just really unrepresented in the past, and really truly new experiences are going to come up, and this is one of them. So the big idea, how to make sense out of this, is to still recall what we understand geometrically about these partial derivatives so far. So this one, still, we're going to think of it as slope of a tangent line, right? Now, it is tempting to, again, sort of cling to the idea, the familiar, satisfying idea of thinking of partials as being slopes, or derivatives in general as being slopes, but we're not going to do that here. This x derivative, I'm not going to think of it as a slope. Mostly because the thing that I'm taking the x partial of, I'm not looking at a graph of it, right? What I'm looking at when I have a graph of a function of two variables, I'm looking at a graph of f. I'm not looking at a graph of the y partial of f. Viewing it as a slope would not be helpful. What I am going to do is view it as a rate of change. That's a familiar point of view. While I'm moving in the x direction. And that's something I can kind of visualize. Let me take you back to, way back here, this point of view on partial derivatives. As I move in a certain direction, keeping track of how much the output changes. Right? So, again, this is not a graph. This is not a level set. This is just thinking in terms of input changes and output changes. Okay. Right. So, here we go. This is the picture we're going to think about. And let me draw some of these things. It's just too bad that these don't quite fit on the page at the same time. But that's okay. Let's talk about the partial of f with respect to y, and here's an example like at this point there, right? As I move in the y direction, I can talk about now keep in mind we're going to visualize the slope of the tangent line. So I'm going to come ... up to where the graph is. I'm going to look at the slope of the tangent line as I move in the y direction, slope of the tangent line to that surface graph. Okay, now, I could also talk about the same thing. Sure, I'll do it. Let me do it here. At that nearby point. Oh, come on. At that nearby point, I could talk about the slope of the tangent line. Now, it's not going to have the same slope of the tangent line. We're at a different point on the surface. The surface is bumpy and wiggly and stuff, and it's different, right? And then likewise, we could look at, let's say, that point. I could come up to that nearby point, and I could look at its tangent line. Okay, so that's all of this stuff that we're looking at here. Color choice. These y partials are those slopes. Note that they are all slopes at different points as I am moving in the y direction. Okay. So how does the x partial show up then if the slopes that I'm looking at are all in the y direction? Well, as we discussed a moment ago, I'm going to think of the x partial as measuring or helping us keep track of how much those slopes are changing as I move in the x direction. Right. So now this is a geometric visualization challenge here. I think the best thing to do is for me to come over to the screen. So this darker red line in the back there, the way I've drawn it, the slope is, I guess, negative. Right. And now you just have to visualize. I mean, three-dimensional drawings are always kind of bad in some way, right? So I'm going to try to make a three-dimensional sort of hand-wavy gesturing of what this shape looks like. We've got a line about like that in the back, and as I come out away from the screen, as I move in the x direction, that slope is going to change. Notice as I come out here to the orange line and then the yellow line. Now look at the slope of that yellow line is positive. And as I'm going in the x direction, as I'm coming out of the screen, these slopes are doing like that. All right, everybody see what I'm talking about here? So then you just have to sort of visualize in your mind what kind of a shape does that. And it's, roughly speaking, if you were to take a sheet of rubber, right, and hold it at the four corners, if you were to kind of twist it like that, you twist it like that, then in the back, see, it's got that negative slope because of how you twisted it. But because of the way you twisted it to get that negative slope in the back, notice that you're going to have a positive slope in the front. Right? So this is what mixed second partials look like in a context like this. This mixed second partial is algebraically a way of detecting how much the surface is. It's so hard to draw. I'm not going to try to draw a twisting surface. I just don't have that kind of artistic chops, right? But it's measuring how much the surface has got a sort of a twist in it. And that's not a concept that exists by any reasonable analogy in single variable. So anyway, I think that's really interesting. It's a little bit of exercise in visualizing partial derivatives. It's also a nice application showing you how important it is that sometimes you really have to think of a partial derivative in terms of not slopes. Right? Think of it as a rate of change as you move in a certain direction. Okay. All right. Side note, this sometimes gets called torsion. A little cultural note. Okay, moving along. So I made the observation at the very start of this that partial derivatives, it's a pro-con kind of a deal. There's a lot of great things about partial derivatives. I do think they're a little overvalued, especially by incoming, new introductory multivariable calculus students, because they're so familiar, they're so easy to calculate, right? And I make the observation that there really is a more natural way to think about derivatives, and we're going to be getting to that reasonably soon. But then I also pointed out that, there's also another neat thing about partial derivatives, and that is lots and lots of other really important things are computed in terms of partial derivatives. And we compute them in terms of partial derivatives explicitly because those partial derivatives are so easy to compute. Right. So anyway, I just want to show you a couple of examples in case in case you're curious. A lot of y'all are engineers, by the way. So these are all kind of engineering, sort of physicsy kind of examples. If you're an econ major, I'm sorry I don't have any good relatable examples. But anyway, if you want to understand what they call electric potential or voltage, or you have some charged particles at various locations in space, perhaps. Y'all know that charged particles create an electric field. correction, if you've had an intro physics class, you know that a charged particle creates something called an electric field. Kind of in the same way that mass creates a gravitational field, right? We walk around in this gravitational field from the Earth, right? No, charged particles do something surprisingly similar. We know that there is this thing called gravitational potential energy. The more you move in a certain direction, that for convenience we call up, the more of this thing called potential energy you have. Well, that's gravitational potential energy. There is also something called electric potential energy. And likewise, there is an electric potential function. So, with charges placed however charges happen to be arranged, you'll want to understand what is the electric potential function. And there's an equation that does that. It's called Laplace's equation, and there it is. And notice it's in terms of partial derivatives. You can see them right there. Okay. How does heat flow? That's a pretty natural question to ask, right? Heat is a pretty fundamental object of interest. And, heat doesn't just kind of get up and walk over there, right? Heat's this weird kind of complicated thing where, like, if I had a fire over on this side of the room, the people real close to here would get hot fast. The people way far away would get hot eventually. Eventually, everyone would be, this room would just be hot eventually, right? So how does that work, right? Exactly in what way does it flow? And it's a complicated question. It's described by this thing called the heat equation, and there it is. And notice that it's in terms of partial derivatives. By the way, this expression here comes up a lot in physics, like a lot in physics. And so we give it a name. We call it the Laplacian operator. And we have a notation for it, the sort of a what you might call a right side up triangle. That little triangle thing, that's a shorthand for the Laplacian operator. So in this next one here, the wave equation, if you're interested in how waves propagate, again, very natural physicsy thing to want to understand. Waves are described by this equation where, notice, everything is written in terms of partial derivatives. So, and then just, last super quick, and this is not a physics class, I just want to, refer to these things. This is called the Schrodinger Equation. This is one of the fundamental equations of quantum mechanics. And depending on your major, you may or may not see a little bit of quantum mechanics here or there. If you're a physics major, you will. But anyway, this is the equation that describes what's the equation of matter, you might say. Okay. And it's got partial derivatives in it in the form of this Laplacian right there. And there's another derivative, time derivative there. So anyway, lots and lots of very physically natural things are all described in terms of partial derivatives. And this is one of the big important facts to know about partial derivatives, is they're extremely useful as a computational sort of atomic kind of tool to use. Okay, so moving along. I want to do a real quick refresher, super quick, on what we call increments and differentials. This is mostly just to make sure we're on the same page about terminology and just to remind you of some super basics. So don't forget, if you have a single variable function, something like that, right? You can talk about at a given point. You can talk about the tangent line. Oh, that's terrible. Let's do better than that. Do better than that. Come on. Okay, there we go. That's pretty good. Tangent line there. And at some point A, that's the tangent line. And then at some nearby point, X, there's a couple of things that you can talk about. On the one hand, you can talk about let me color code. You can talk about the value of the function at that nearby point, but then you can also talk about the value of the linear approximation at that nearby point. And notice they're not the same. Right? Okay, so that in mind, A little bit of terminology. Oh, and by the way, just I made sort of an unfortunate choice in writing this down. Y'all know that there's a bunch of different ways that you can sort of choose to denote a point and a nearby point. Here I just made a different choice, and for consistency with what comes below, let me just make this change to consistent with what I have there. That's x, and this, let's call this a. Right, so this difference, f of x minus f of a, let me, again, make a better color choice. F of x minus f of a, that's what we call delta f, and that's known as the increment. So that's that. Delta f. Okay, don't make the mistake of confusing that with what we call the differential. The differential is, so again, I have to change the back to be consistent with what comes next. The difference is not the change in the value of the function. Here we're going to be looking at the difference in the value of the linear approximation. And, right, so this thing, L of x minus L of a, this is what we call the differential. Okay, so I know y'all know this. I know you've seen this kind of picture a million times back in Calc 1 classes. So I want to make sure we're all on board, though, about the terminology. So increment and differential. Differential is just a linear approximation of the increment. Let's say, therefore, a tool for estimating the value of the function. Okay, so now let's just talk about a multivariable version of this. Suppose I have a function of two variables. By the way, I'm not even going to draw a picture. I don't really need to draw a picture. I mean, I guess I could draw a graph, but why, right? What's the point? We already know the formula for the linear approximation. The formula for the linear approximation of a multivariable function is this. And we talked about that last time, I guess it was. Yeah. Okay. All right, well, remembering that in some sense the whole point of a tangent line is that the value of the linear approximation is the exact same as the value of the function, right? L of x minus L of a is the same as L of x minus f of a. In other words, I can write the formula for the differential. This differential is just, well, it's the difference between those two things. And that differential then, because these are the same, well, anyway, those are the same, is just all the rest of this stuff here. Yeah. Yep.
Isn't that also the equation of the tangent plane that I'm avoiding?
Well, it's the function whose graph is the tangent plane, right? But it itself is a function of two variables. But you got to say graph if you want to actually talk about the tangent plane. So
is there some sort of relation?
Yes. So a function is not the same as its graph. That's the...
No, but between linear approximation and the tangent plane?
Yes, the graph of the linear approximation is the tangent plane. Okay. That's right. Yeah. Okay. Yeah. So, now, so this is just, you might argue that what I've written down here is really just kind of a different way of saying, again, something we already knew. I'm motivating the idea of calling this thing here the differential. That's just, again, the linear approximation of the increment, or the linear approximation, and how much does the function change. And then just notice I can rewrite this. Just happens to, neat fact. This formula right here is a product, it's a sum of products. It's these things multiplied and then added to with those things. Right? So it's literally a dot product. That's just an observation. There it is. That's the algebra. How about that? Happens to be a dot product. Now, next observation I want to make real quick is that this thing that I wrote down, that's actually pretty natural in the domain. That is x minus a. That's the x vector. You can see it right here, right? The x vector is those coordinates, and the a vector is those coordinates. This is literally the vector x minus a, which, by the way, you might pretty naturally rewrite as dx. After all, that's what we're doing with x and a. A is a point where I'm starting and where I'm computing various derivatives, doing my linear approximation, and then x is a nearby point that I'd like to understand better. Right? So x minus a, this is how much I'm planning to change my input. And so now look at this formula has actually simplified pretty nicely. df is this thing here. Oh, by the way, let me come back up here. This thing here, we have a notation for it. We're going to write it like that. We're going to call it the gradient of the function. It's that thing dot dx. Now let me say that a little bit different. Same statement. This thing is the thing that I multiply by an input differential to get my output differential. That rolls off the tongue really nicely, doesn't it? Right? In fact, that's one of the critical features of single variable derivatives. If you think about it, right? That's what single variable derivatives do. The all-encompassing, as I observed, very first time we started talking about derivatives, what derivatives fundamentally are is relationships between input changes and output changes. That's what this green thing is doing. That green thing is a relationship between input vectors and input differentials and output differentials. So this thing is fundamentally interesting then, right? It is playing the role of the derivative in this multivariable context, where we have multiple input variables. So this thing, I'm going to go ahead and talk about the name now. It's called the gradient. It's another of several different more types of derivatives that we're going to talk about in this class, right? So the gradient of a multivariable function, written like that, is this vector made up of all the partial derivatives of that function. And we're interested in it because, again, it plays the role that derivatives are supposed to play in a role like this, in a situation like this. Okay, so I think that's super interesting. So this is by the way, kind of a first example of why I'm a lot less excited about partial derivatives than I am about things like this gradient vector. This is a truly multivariable concept. I mean, no kidding. This is not, it's multivariable, I suppose, in a sense, but I can only make sense out of it if I pretend it's single variable. That's what partial derivatives are, right? Partial derivatives say, oh, you've got a multivariable function. Okay, step one, let's pretend it's single variable, and then let's do single variable calculus. That's not what this is. This gradient vector, a truly multivariable derivative, because I'm not pretending anything. You give me any input differential, whatever this input differential is, whatever, any vector. This gradient vector tells you the corresponding output differential. Yeah, so that's a very valuable thing. Okay. Side note. Now I only wrote down the formula here for gradients for functions of two variables, just to kind of, ease of notation, writing this down. But recall, we have a formula for linear approximations for any number of input variables. It's just more terms that look just like that. You can write down the same sort of development, and you can generalize to when you have more input variables. You just have, it remains that your gradient vector just consists of, it's a vector consisting of all of the partial derivatives of the function. Okay, so, yeah. If you're going to hang your hat on one concept of multivariable derivatives, this is a better candidate than partial derivatives. It is, in fact, a multivariable derivative in a multivariable sense. Partial derivatives aren't. So, okay, all right. All right, and I have a better candidate coming up. Probably not today, but sometime, certainly by Wednesday. Okay. All right, so a quick example. Let's just get our hands dirty. Y'all remember problems kind of like this, where you need to estimate the value of some function, but the problem is that those particular numbers are super inconvenient to deal with, and so I can't compute it exactly, but can I estimate what this thing is? And the point is, you do a linear approximation, right? So that's all I'm going to do here. I'm going to do a linear approximation. There it is. There's our formula for differentials, right? Excuse me. Notice that the thing we're trying to estimate looks like a value of that function near this point where this function evaluates really nicely. Little exercise, plug in x equals 3, y equals 0, everything computes up real nice. Okay. But I'm not actually at that point. I'm actually interested in this point over here. I'm actually interested in when x is 3.02 and y is 0.01. And what you'll notice is that x that I'm interested in is that 3 that I like plus that dx. And the y that I'm interested in is, well, it's this 0 that I like plus that dy. Right, so very familiar sort of a setup. I've rewritten a numerical calculation as a multivariable function with a point that I like and then a very small differential to get to the point that I actually care about. Okay, and that's all plug and chug from here. The gradient. We have a formula for gradient. It's partial derivatives. Y'all know how to compute partial derivatives. Plug and chug. By the way, I am going to assume at this point that y'all are snappy, proficient, solid on computing partial derivatives. If you are, by the way, perhaps a little rusty on your single variable derivatives. If it's been a while, whatever the case may be. Definitely want to polish off those mechanics, those skills, and make sure that you can crank out single variable derivatives quickly and reliably. Okay. Let's see here, our dx vector, right there. And so plug in some numbers. Of course, we're evaluating this gradient at the point A. Let me do it like this. At the point A, so these numbers are what's going to plug into there, which makes our gradient expression turn into that. And we've got a really easy little calculation here. Multiply I'm going to say the derivative times the differential, just like in single variable calculus. It's just that now the derivative is a vector, the differential is a vector, and times is a dot product. But still, it's derivative times differential. So, yeah. Okay, a little bit of arithmetic. And now don't forget what we've computed there as a differential. Right, so all of this business that we just computed is df. It's not actually the value of the function. You have to actually add in the value of the original to your base point, if you will. Don't forget to add that in. That's 2. And so altogether, our estimate of the value of the function is that. And now just for your reference, how well did we do? Well, the calculator says that it's approximately that value, and notice it's pretty close. I mean, that's respectable. Okay. All right. Yeah, so moving along. So this next page represents an awkwardness about this course. Oh, gosh. Okay, so this being a multivariable calculus course, we have to talk about derivatives. Well, of course we do. If you can take a derivative, we're accustomed to the idea that if you can take a derivative, the word is differentiable. So, seems like a reasonable thing. I should just tell you what the word differentiable means. Doesn't that seem like, well, of course, we should talk about what it means for a function to be differentiable. And it turns out that's a hard conversation. There's some surprisingly deep weirdness that happens with multivariable derivatives. You remember how I was saying that some things in multivariable calculus some things are just like single variable calculus, just, a little different. Like this calculation here, it's just two variables of the same thing we did in Calc 1. Right? It's just linear approximation. It's just derivative times differential gives you differential. But some things really are fundamentally, importantly different, and ways for which there is no equivalent in single variable calculus. And it turns out that there's some ugliness, there's some real nasty little hidden little detail devils when it comes to differentiability and multivariable calculus. And we're not going to talk about that in this course, right? If this were Math 222, we'd talk more about that kind of thing. Okay, so let me first hit the broad stroke of here's what you actually need to know in a class like Math 212. The first thing I need for you to understand is this thing called continuous differentiability. Continuous differentiability. So a function is continuously differentiable if it satisfies two conditions. All of the partial derivatives have to exist. That's the first thing. And furthermore, they have to all be continuous. All right, so thus the name continuously differentiable. I think that seems like a pretty plausible. This definition is highly analogous to what it means in Calc 1 for a function to be continuously differentiable. It's differentiable, the derivative is continuous. Exactly what you would expect. Okay. Easy to check, by the way, because partial derivatives are easy to compute. Do they exist? Well, plug in at the point you're interested. See if it exists, right? I mean, that's very straightforward. And continuity, again, most of the time, it's easy to check. We have a convenient rules for that back in the section on limits. Okay, so this is great news. Continuous differentiability is easy to check. Here's another neat fact about continuous differentiability. And that is, if a function is continuously differentiable, then that function is also differentiable. I have yet to tell you what differentiability means, right? And this is where I'm going to have to start sweeping stuff under the rug. Differentiability means roughly this, all this stuff. And even this is very, very, very quick and dirty. And we just don't have time to go into those details, right? So, well, that's frustrating. Why do we need differentiability? Natural question to ask. And, well, just so you know, differentiability is important as follows. Differentiability specifically is the exact right condition necessary for stating lots of important theorems. Lots of stuff that we're going to do in this course. What is the strict requirement necessary to use that theorem that we're going to be using later in the course? The function must be differentiable. That's what we need, right? So in practice, here's how you're going to do business. In practice, you're going to do the following. You're going to say, okay, well, I'm going to check that the function I'm dealing with is continuously differentiable. Once you know it's continuously differentiable, you're going to conclude, well, therefore, because it's continuously differentiable, it must be differentiable, and because it's differentiable, I get to use my theorems that I want. Right? That's what you're going to do in practice. Okay. All right. Now, this naturally brings up a question. Well, if continuous differentiability will always let me use the theorems that I want, why are we even talking about this thing called differentiability? And it turns out that there are some functions that are differentiable, but which simply are not continuously differentiable. So if you restate all these theorems down here as just check continuous differentiability, you're shooting yourself in the foot. There are cases where you'd like to be able to use those theorems, and where the function is merely differentiable, it's not continuously differentiable, and our little shortcut strategy of just checking continuous differentiability just isn't going to help us. So that's the deal there. That's why this little problem exists. Okay, so very quickly, what does differentiability mean? Let's talk about that. And again, I'm not going to go too hard on this, but I think this is pretty satisfying. It means that that when you do linear approximations, then you get what I'm going to call good, that's very vague, good approximations to the increment. This is where the detailed devils are. What I mean by good is a long conversation, and we can't go into that. But it turns out that there are some cases of functions that are weird in certain ways, but still have this nice feature. A different way to think about it, if you prefer, a function is differentiable if the graph of the function has a tangent plane that I will loosely again call a good tangent plane. Well, you got to be. What's the difference between a good tangent plane and a not good tangent plane? And well, again, long conversation ensues there, but there's some really subtle business in there as well. So, I mean, and then by the way, if you want to write these down rigorously, here's how you do it. This is a definition. A function is differentiable. You'll find this definition in the book. If there exists some vector C that has the property that it makes this limit always equal to 0. And why this is the definition is, again, a long conversation, and it's a lovely conversation, but we don't have time for it. Anyway. All right. So I want y'all to see what differentiability is. I want you to know that there's subtleties around it. And I also want you to know that in practice, day in and day out, you're going to be doing business with continuous differentiability because it's so easy to check. And knowing that, then that allows you to use the important theorems even if you've technically checked something stricter than was necessary. Okay. All right. Does anybody have any questions on this before I go on? This stuff just kind of has to get said. If you want to have a longer conversation about this, you're very welcome to come talk to me in office hours. I can get into the ugly. It's actually very beautiful ideas, but anyway, it's going to seem ugly. So feel free. Okay, so all of that done. Okay, we've got plenty of time. Good deal. We're going to go on to the next section, talk about the chain rule. So let's start with you have here a function of two variables, right? I'm going to give a name to the output variable just to have a name for it. We don't have to think about this in terms of graphs. I know that looks like the equation for the graph. I just want to have a name for the output variable. And given a function of two input variables, here's our formula for the differential. It's just, writing that. Here. We're writing this formula back here in a different way. This formula back here in a different way. Don't forget, this is made up of a bunch of partial derivatives. So that dot product dots out to this. There's the gradient, and here's, I'm dotting with the input differential. Okay, now, let's precompose this function. Let me remind you, we have this function here, f from R2 to R1, z is a function of x and y. I want to take this function that I've already got differentials written down for. I want to precompose with another function. I want to think of its input variables, x and y, as being functions of t. So you can see I'm composing these functions. Z is a function of x and y. X and y themselves are functions of t. Okay. And y'all recall, whenever you compose functions, there's a question about, okay, well, what, can I talk about the derivative of the composition? How would I compute the derivative of the composition here? If I wanted to view z as being a function of t, right? Just, just do the composition, combine those functions together. What's the derivative of that function? Very reasonable question. And good news, it's real easy to compute. The clever move, and by the way, I'm totally going to sweep details under the rug here, formalities that y'all won't need to worry about, but I think the following is very satisfying. If you're interested in computing that, just take this initial formula that we already had. There it is. And let's just divide by dt. right? And check it out, we have ourselves an answer. And again, I'm committing little math crimes, and it's nothing we need to worry about in this course. But this composition, that derivative of that composition, I've got written as, you will notice, the derivatives of the first function, well, the function we started with. It's second in the composition, of course. And how I algebraically relate those to the derivatives of the precomposed functions. So this is really, really analogous to the chain rule that we saw back in single variable calculus, right? In single variable calculus, what's the derivative of the composition? Well, it's the product of the individual derivatives. That's kind of what we're doing here. It's just that there's two terms instead of one term. But you can see it right there. The green derivatives times the yellow derivatives. I mean dot product in times, not calc 1 times, right? But still, the composition is the product, in a sense, of the individual derivatives. Very believable, very satisfying. Okay, so now I'm going to give you a different point of view on this. I think this is very valuable. The way you're going to use the chain rule in practice, sadly, the world is just not always set up with these exact choices of variables. It's not always z being a function of x and y being functions of t. It might be, it could be p is a function of n and a, both of which are functions of q, right, or whatever. And there are other situations where it's just, having a memorized single formula is just not a good tool to work with. So what I'd like to do is give you a different sort of instinctive interpretation of where this formula comes from and why this formula sort of ought to be true. I think this is very satisfying. Here we go. What we are interested in doing is asking, well, if I were to change t by a little bit, how much does z change? And I'm going to put in an input change to t, and I want to know the output change to z. Okay. So, in some sense, I want to know, how much does change get magnified if I go from a t change to a z change? I'm just speaking loosely. Okay. Well, the point of view that I want to propose is that the change that I start with, this t change down here, is going to propagate along two different paths. Right? So let's start with this one. When you change t, you're going to also be changing x. And furthermore, when you change x, that change in x is going to cause a change in t. So this is what I call a propagation of change along a path. Right? And now, by the way, also, when you change t, that's going to simultaneously cause a change in y, which, when you change y, that will also cause a change in z. So, to shorthand it, the change that we're interested in is going to propagate along these two different paths. And now let's just think through each path kind of one at a time. Let's start with the one over here on the left. Let's start with, how does change propagate through x? Okay. Well, we know what happens if you change t, and you want to know how much does x change. We have an answer to that question. The answer is the change gets magnified by a factor. That factor is the partial derivative. Well, it's there's only one input variable. That's the derivative. That's what dx dt is. It's the factor that tells you how much these changes get magnified by to turn into those changes. Yeah? That's single variable calculus. Okay. So I'm going to say that in going over that arrow, we get a factor of dx dt. Okay, now, here's the thing, though. So that tells you how much x changes, but I also want to know, given an x change, how much does that change in x grow by to turn into how much z is changing, through that path? Well, we have an answer to that question as well. The relationship between x changes and z changes, how much the change magnifies along that path? Well, it's the partial of z with respect to x. That becomes the next factor, right? So this change, when you change t a little bit, it gets magnified by dx dt, but then it afterwards also gets magnified by partial of z with respect to x. And check it out. That's exactly this first term. Right, so this first term represents how much of the derivative, how much of the magnification comes from propagation along that x variable. I think that's very natural. And now, of course, once you've thought it through this first time, the next time you need to do something like that, you say, okay, well, look, as I go along there, I've got partial of x with respect to t times partial of z with respect to x. I mean, you know what the factors are. You can see them right there in your picture, so you don't have to sort of think it through from first principles every time. You can just see these factors right there in the variables that you're moving between along that path. Everybody good? Okay. So along this path, well, same argument. dy dt partial z with respect to y. So altogether then, I mean, you can think of this formula, you can think of it as coming from gradients and linear approximations, which is kind of where we wrote it down in the first place. Or I think, depends on your perspective, maybe a little bit more intuitively, this formula is an observation about how changes propagate along these two different paths that between the two of them connect z to t overall. Yeah, there you go. Okay, so nice. I think it's a really nice point of view. Again, it has some real big advantages that we're going to use this point of view a lot going along. By the way, just for terminology, these variables, I call them intermediate variables because they're sort of intermediate between t and z as you sort of move from t to z. Okay. All right. Let's see an example. Suppose you have z as a function of x and y, each of which then is a function of t. Yeah. So here we have a composition, right? Altogether, z is a function of t, but yeah.
Are those x equals goes to y? Those will just be given. Right?
No comment. This is a scenario. So sometimes they are, sometimes they aren't. In this first application, they're given, but you can't always assume. Yeah, no. Sometimes I want to see if you understand the chain rule, and I'll test it by giving you some parts of the story, but not others. And the point is that this is something that's always true, right? And then how you apply it depends on the circumstance. Yeah, right. Okay, so we have a composition, and notice all you got to do is compute some partial derivatives, right? The partials of z with respect to x and y. Cool. That's where they go. The partials of x and y with respect to t. I mean, they're not even partials. Those are regular old derivatives. Easy to compute. There they go, and here is your overall composition derivative dz dt. Okay. I will point out you could, in a sense, I suppose, oh boy, this would be ugly. You could take this and plug it into there, and you could take this and plug it into there and into there, and rewrite z as this great big function of t. And then use single variable calculus and the single variable chain rule to power your way through it. Right? So that would get you to an answer that would not be false. Right? Okay. So I want to address this option though. Let me just remind you, this is a perspective change that I know is kind of hard to pull yourself out of, but in a high school class that might have been considered, okay, well, it's all about the answer, so you got the right answer, and hey, it's free country. Right? That's not what this course is. This course is not about answers. This is not. This is a course about ideas. Right? So, on an exam, if I were to give you, this given and ask you, to compute that thing, here's the line of reasoning that you should think of. You should think, okay, well, why would he ask me this question? What's the point of this question being on the exam? So you want to make sure that I'm really good at hardcore single variable calculus? Is that the purpose of this question? No, of course not. That's not what this is. This isn't a single variable calculus class, right? I would put a question like this on an exam because I want to make sure that you understand multivariable calculus ideas, right? And so you should realize, and by the way, I talked about this on the webpage as well, in the class website. Part of the question is to interpret what is the purpose of the question, what ideas am I testing, and then demonstrate what I want you to demonstrate. Right? Again, it's not about the answer at the bottom of the page. It's about demonstrating the ideas that we're interested in. So you should infer from the question then that, well, I don't want you to just plug in, make it a single variable function, and just take a deep breath and plow. It's not what we're here for. Right? Okay, so be aware that's the case. This is that's what you're responsible for on an exam, and specifically, if you were to turn this into a single variable calculus problem on an exam, don't expect a lot of credit. It's absolutely not what this course is about. So, okay, all right. Good place to draw a line. We'll pick up here next time. See y'all later.